In this video, we will discuss the basis and dimension. First, let us define a basis for a vector space. A set of vectors S containing v sub 1, v sub 2 up to v sub n in a vector space V is called a basis for V if the following conditions are true. First, S spans V and S is linearly independent. Recall that a set S spans V if every vector in V can be written as linear combination of vectors in S. Also, S is linearly independent if the vector equation C sub 1 times V sub 1 plus C sub 2 V sub 2 plus and so on up to C sub n times V sub n equals 0 has only the trivial solution. So do not forget those two ways to show that S spans V and S is linearly independent. The standard basis for n space. So the following vectors form a basis for Rn called the standard basis for Rn. So we have E sub 1 equals 1, 0, 0 and so on. E sub 2 is 0, 1, 0, 0 and so on. And E sub n equals 0, 0 and we have 1 in the nth coordinate or nth component. Next, the standard basis for P sub n. This is the polynomial, the set of polynomials of degree n or less is the set S containing 1, x, x squared, and so on up to x raised to n. Moreover, the standard basis for the vector space M sub m n, this is the set of m by n matrices, consists of the m times n distinct m by n matrices having a single 1 and all the other entries equal to 0. Now let us have some examples of bases for a vector space. So first, show that the following set is a basis for R3. So we have the given set S. So again, this set S is a basis for R3 if S spans R3 and S is linearly independent. In our previous lecture video, we have shown that this set S spans R3. Now, since this vector equation, has only the trivial solution, we have C sub 1 equals C sub 2 equals C sub 3 equals 0, then S is linearly independent. So it follows that S is a basis for R3 and is called the standard basis for R3. Next, let us show that this set S is a basis for R2. So first, we show that S spans R2. So we want to show that each vector in R2 can be written as linear combination of these vectors in S. So we let X be an arbitrary vector in R2. This can be written as linear combination of these vectors in S, the V sub 1 and V sub 2. To do this, we need to find the scalars C sub 1 and C sub 2 such that we have this. This is equal to our X sub 1, X sub 2. Then we substitute the given vectors, V sub 1 and V sub 2 here. So that we have, okay, by adding these two, we have this. So we get the linear system C sub 1 plus C sub 2 equals X sub 1 and C sub 1 minus C sub 2 equals X sub 2. Since the determinant of the coefficient matrix of this linear system is, we have 1 times negative 1, so that's negative 1 minus 1, that's negative 2, which is non-zero, then we say that the system or this system has a unique solution. Thus, this set S spans are 2. Next, we will show that S is linearly independent. So we have, okay, so this equation, so we want to show that we have only the trivial solution for this equation. So again, we substitute the values for the vectors v sub 1 and v sub 2, and then we add this, so we have this equation. And so we have this linear system. Since again, the coefficient matrix of this system is non-zero, or the determinant of the coefficient matrix of the system is non-zero, so it has a unique solution, which is the trivial solution c sub 1 cos 0 and c sub 2 equals 0. Therefore, we say that S is linearly independent. By the way, you may also use the idea that since these vectors are not scalar multiples of each other, then the set S is linearly independent. This was introduced as a corollary in the last part of the previous chapter or lesson. Another example is we have the set S containing these matrices is a basis for M22 and is called the standard basis for M22, the set of 2 by 2 matrices. So observe that the basis S contains 4 distinct 2 by 2 matrices with a single entry 1 and all other entries are 0. So this is the basis for M sub 22. You can show in similar manner as in the previous examples that S spans M sub 22 and S is linearly independent. And so this is the basis for M sub 22, the standard basis for M sub 22. Now next we have the uniqueness theorem of basis representation. So if S is a basis for a vector space V, then every vector in V can be written in one and only one way as a linear combination of vectors in S. So for the proof, so note that the existence of the linear combination follows since S spans V, so we know that for an arbitrary U in V, you can express U as we have Cn times the vector V sub n. Okay, again, these C sub 1, C sub 2 up to C sub n are scalars. Now, to prove the uniqueness of representation, we suppose that U has another representation. Say, U is equal to V sub 1, V sub 1 plus V sub 2, V sub 2 plus V sub n, V sub n. Okay, so again, we assume that we have another representation for, or a linear combination for U. So subtracting these two equations, you will get U minus U, which is equal to C sub 1 minus V sub 1, V sub 1 plus C sub 2 minus V sub 2, V sub 2 plus, and so on, plus C sub n minus V sub n times V sub n. And then we subtract the second equation from the first equation. So this is equal to 0. So again, this is equal to the 0 vector. Now, since S is linearly independent, then the solution to this equation is trivial. That is, your C sub 1 minus B sub 1 is 0, C sub 2 minus B sub 2 is 0, and so on, 2C sub n minus B sub n equals 0. Thus, we say from these equations that C sub I is equal to B sub I for all I equals 1 to up to n. Therefore, from this, it follows that U has only one representation for basis S. Now let us show this theorem in an example, this next example. So we let U be this vector, any vector in R3. Show that this equation has a unique solution for the basis S given as the set. So for the solution, first we substitute this given set S or these vectors in this equation. So we have, okay, which is equal to this one, which is equal to this. So that from here we form the linear system with the unknown C sub 1, C sub 2, and C sub 3. And from this, we write down the augmented matrix of the system. So we have here 1, 0, negative 2, U sub 1, 2, 1, 0, U sub 2, 3, 2, 1, U sub 3. And then let us try to use Gaussian or gauss-jordan elimination to solve for the given system. So this implies we will make these zeros. So we have, okay, we multiply row 1 by negative 2 and then add to row 2 to get new row 2. So this is 0, negative, this is 1, that is 4, and then this is negative 2u1 plus u sub 2. And then we make the 0 by multiplying row 1 by negative 3 and then add to row 3. So that's 0, we have 2, that's times negative 3, so that's 6 plus 1, so 7, negative 3 u sub 1 plus u sub 3. Then proceed, we will continue the process until we get the reduced row echelon form. So 1, 0, negative 2 u sub 1, 4, negative 2 u sub 1 plus u sub 2. We make this 0, we multiply row 2 by negative 2 and then add to row 3. So that's 0, that's negative 1. So we multiply this by negative 2, so that's 4 minus 3, so that's u sub 1 minus 2 u sub 2 plus u sub 3. Okay, and then we can make this positive 1 by multiplying by negative 1. 1, 0, 1, 4. So negative 2 u sub 1 sub 2, 0, 0, that's 1. Negative u sub 1 plus 2 u sub 2 plus, sorry, that's minus u sub 3. Okay, and the next we can make these two entries above this one 0 by, first we can multiply the third, sorry, this is 0, 1, negative u sub 1 plus 2 u sub 2 minus u sub 3. By the way, you can stop here, you can just can use the back substitution to solve for the C sub 1, C sub 2, and C sub 3. Or we can continue and we make this in reduced row echelon form. So we will make these two zeros here. So we have 1. We can multiply this by negative 4 and then add to this one. So this becomes 0. Again, we multiply by negative 4. So this becomes 4 u sub 1 minus 2 u sub 2. So that means we have 2 u sub 1 and then times negative 4. So that's negative 7 u sub 2 and then times negative 4. So that's 4 u sub 3. Okay. And then next, we have the first row. Okay, so this is 1, 0. We multiply this third row by 2 and then we add to row 1. So this is 0 now. Multiplied by 2, so plus, so that's negative u sub 1. And then plus 4 u sub 2 minus 2 u sub 3. Okay, so from here, we now get the solution for c sub 1. We have c sub 1 equals negative u sub 1 plus 4 u sub 2 minus 2 u sub 3, and c sub 2 equals 2 u sub 1 minus 7 u sub 2 plus 4. C sub 3 equals negative u sub 1 plus 2 u sub 2 minus u sub 3. Okay, so we have here the solution for c sub 1, c sub 2, and c sub 3. Now, for instance, say our u, we select u as 1, 0, 0. Then we say that u is equal to, we substitute these values for u sub 1, u sub 2, u sub 3 to get the solutions c sub 1, c sub 2, and c sub 3. So therefore, u will be just, your c sub 1 will be negative 1, so negative v sub 1, then plus, again, this will become zeros here, and then we have 2, so our c sub 2 is 2, v sub 2, and then plus, or that's minus, we have negative 1 here, so we have negative v sub 3. So we have shown that each u in R3 can be written in one and only one way as a linear combination of these vectors in S. Now let us have the following two important theorems. So if S is a basis for a vector space V, then every set containing more than n vectors in V is linearly dependent. Okay, so if the set S contains only n vectors, so every set that contains more than n vectors in V is again linearly dependent. Next is, if a vector space V has one basis with n vectors, then every basis for V has n vectors. So if you have 5, for example, vectors of you have n vectors in one basis, 5 vectors in one basis, then every basis must have also 5 vectors. So for example, we have here the set S sub 1 containing these vectors is not a basis for R3. Why? Note that the standard basis for R3 consists of 3 vectors. The vector 1, 0, 0, vector 0, 1, 0, and 0, 0, 1. However, this S sub 1 here contains only 2 vectors. So this S sub 1 cannot be a basis for R3 from this theorem. Similarly, this set S2, S sub 2, containing these vectors is not a basis for the polynomial of degree 3 or less, since the basis for P sub 3 consists of 4 vectors. We have 1, x, x squared, and x cubed. But this one has 5 vectors, so this can't be a basis for P sub 3. Next, we proceed with the dimension of a vector space. If a vector space V has a basis consisting of n vectors, then the number n is called the dimension of V. That is denoted by this. If V consists of the 0 vector alone, the dimension of V is defined as 0. So the following are the dimensions of the familiar vector spaces. We have the dimension of Rn with the standard operations is n. Next, the dimension of P sub n. This is a polynomial of degree n or less with the standard operations is n plus 1. And the dimension of the set of m by n matrices with the standard operations is m times n. Note that these dimensions are determined by simply counting the number of vectors in their standard bases. Now we note that if W is a subspace of an n-dimensional vector space, then it can be shown that W is finite dimensional and the dimension of W is less than or equal to n. And determining of the dimension of W is done by finding a set of linearly independent vectors that spans the subspace. This set is a basis for the subspace, and as in a vector space, the dimension of the subspace is the number of vectors in the basis. Let us have some examples in finding the dimension of a subspace. So first, we determine the dimension of each subspace of R3. So first given, we have W. Okay, the subspace W containing the vectors D, C minus D, C, where C and D are real numbers. So for the solution, now we take note that the representative vector D, C minus D, and C can be written as, we can have 0, C, C, plus D, negative D, 0. Okay, we just write the vectors as this vector as a sum of vectors. One contains C and the other contains D. But when you add these two vectors, it will result to this one. And then if we factor out this C, so we will just have C times 0, 1, 1 plus we have D, 1, negative 1, 0. So from this, we see that W is spanned by the set S, which is equal to the set or containing the vectors. We have 1, negative 1, 0. Moreover, since these vectors are not scalar multiple of each other, then this set is linearly independent. Thus, we have shown that we have W is spanned by the set S, and S is linearly independent. So we say that S is a basis for W. So W is a two-dimensional subspace of R3 since the basis has two vectors. So again, the dimension of the subspace W is determined by counting the number of vectors in its bases. Now let us try this next given for W. So W is the set containing the vectors of the form 2b, b, 0, where b is a real number. So the representative vector, we have 2b, b, 0 can be written as b, 2, 1, 0. So W is spanned by the set, the set S containing 2, 1, 0. Okay, and since we have only one vector here, so this set is linearly independent. Therefore, W is a one-dimensional subspace of R3. So we consider this one as a basis for W. Okay, so containing only one vector, so therefore W is a one-dimensional subspace. Another example, we have find the dimension of the subspace W of R4 spanned by this given set. So note that even though S spans W, this does not mean that S is a basis for W. We have to check first if S is linearly independent. So to do this, we need to solve for C sub 1, C sub 2, C sub 3 in the equation C sub 1, V sub 1 times plus C sub 2, V sub 2 plus C sub 3, V sub 3 equals the 0 vector. Okay, so these are vectors. Okay. So if we substitute the vectors, we have C sub 1, negative 1, 2, 5, 0, plus C sub 2. We have V sub 2 is 3, 0, 1, negative 2, plus C sub 3 times negative 5, 4, 9, 2, which is equal to the 0 vector. Okay. So from here, we can now create our linear system. So we can just add the results after multiplying these scalars here. So we have negative C sub 1 plus 3, C sub 2 minus 5, C sub 3, sorry, let us make it clear, 5 equal to 0. And then another one, we have C, 2 C sub 1, we have 0, so we have plus 4 C sub 3 equals 0. Then 5 C sub 1 plus C sub 2 plus 9 C sub 3 equals 0. And lastly, we have negative 2 C sub 2 plus 2 C sub 3 equals 0. And then we get the augmented matrix of this linear system. So we have negative 1, 3, negative 5, 0, 2, 0, 4, 0, 5, 1, 9, 0, and then 0, negative 2, 2, 0. Okay, then by applying row elementary operations, so that matrix will now become, we can multiply this by 2 and then add to row 2. So that is 0. We have 6, negative 6, 0. And then we multiply this by 5 and then we add to row 3 to get new row 3. So that is 0. So 16. That is negative 16 and then 0. And then copy that. We have 0, negative 2, 2, 0. Okay, and then we can further simplify this. We can just have 1 here. Implies, or we have a, okay, so we have 0. We'll make this 1 by dividing or multiplying by 1 over 6. So 1, 1, 0, multiply by 1 over 16. So that's 1, negative 1, 0, multiply by 1 over 2. That's negative 1, 1, 0. And that is equivalent to, we can just subtract these 2 and then we can add these 2 to have a new row 4, row 3 and row 4 rather. So we have 0, 1, negative 1, 0. We have 0, 0, 0, and then 0, 0. Okay, so this implies that the system has infinitely many solutions, and so S is linearly dependent. So if we let C sub 3 equals T, so let C sub 3 equals T, and solve for C sub 2 and C sub 1, we get, so from here, that is, we have negative C sub 3 transposed on the other side. So C sub 2 is just equal to T also. And C sub 1 is equal to, we substitute T here. So that's negative 2T. Okay, transpose it on the other side. So therefore, C sub 1 is negative 2T, where T is any real number. But if we are going to let T, for example, equal to 1, then we will get C sub 1 as negative 2 or equal to negative 2, C sub 2 equals 1, and C sub 3 equals 1. So by substituting these values of C sub 1, C sub 2, and C sub 3 to this equation, we have now negative 2 V sub 1 plus V sub 2 plus V sub 3 equals 0. Okay, which implies that V sub 3 is equal to 2V sub 1 minus V sub 2. So we say that we have W is spanned by the set S sub 1, which is equal to V sub 1, V sub 2. These are the vectors negative 1, 2, 5, 0, and 3, 0, 1, negative 2. Okay, and S sub 1 is linearly independent since neither of these two vectors can be written as a scalar multiple of the other. Thus, W is two-dimensional. Because again, this S1 is a basis for W containing two vectors. Next example, we have let W be the subspace of all symmetric matrices in M2 sub 2 or M sub 2, 2, the set of 2 by 2 matrices. What is the dimension of W? So again, W is the subspace of all symmetric matrices in M sub 2, 2. Note that the 2 by 2 symmetric matrices are of the form A, B, B, C. Okay, so symmetric, these two must be the same. Okay, and this matrix, 2 by 2 matrix, symmetric matrix, can be written as A 0, 0, 0 plus we separate the matrix containing B, and then plus last one, the matrix containing C. Okay, so again, when you add these three matrices, the result will be just this matrix. And then we factor out these real numbers, A, B, and C. So what is left? We have 1, 0, 0, plus we have B, 0, 1, 1, 0, plus C, 0, 0, 0, and then we have 1 here. Okay, so the set S containing the matrices 1, 0, 0, 0, 1, 1, 0, 0, 0, 0, 1 spans W. Also, it is easy to see that the solution to the equation, let's write it. The equation, we have c sub 1 times 1, 0, 0, 0 plus c sub 2, 0, 1, 1, 0, c sub 3, 0, 0, 1, 0, 0 is only the trivial solution. Therefore, the set S is linearly independent. Thus, the dimension of W is, we have 1, 2, 3 vectors, so we have 3. Now we have a basis test in an n-dimensional space. Let V be a vector space of dimension n. If S is a linearly independent set of vectors in V, so S contains n vectors, then S is a basis for V. Also, if S, again containing n vectors, spans V, then S is a basis for V. So to check if a set S is a basis for a vector space V, we show that S satisfies the two conditions. We have S spans V and S is linearly independent. However, this theorem tells us that if the vector V is known to have a dimension n and the set S has n vectors, then it suffices to show only one of the two conditions. Either you show that S is linearly independent or S spans V. So for example, show that the set of vectors is a basis for the 5 by 1 matrices. Okay, so we have the given S. Observe that this set S has 5 vectors, and we know that the dimension of M sub 5, 1 is 5 times 1, which is equal to 5. So by the above theorem, to show that this set is a basis for M sub 5, 1, we can show either this set spans M sub 5, 1 or this set is linearly independent. So we have, by solving the equation, we have 5 vectors. So we have this. So by solving this equation, we can obtain the linear system C sub 1 equals, have here, C sub 1 equals 0, and 2C sub 1 plus C sub 2 equals 0. We have negative C sub 1 plus 3C sub 2 plus 2 plus 2C sub 3 equals 0. Also, we have 3C sub 1 minus 2C sub 2 minus C sub 3 plus 2C sub 4 equals 0. And lastly, we have C sub 1, 3C sub 2 plus 5C sub 3 negative 3C sub 4 then minus 2C sub 5 equals 0. So since this system has only the trivial solution, because C sub 1 is equal to 0, when you substitute that in here, C sub 2 is equal to 0, and so on. So we have only the trivial solution, then the set S is linearly independent. So since it is linearly independent and it has 5 vectors, then we say now that S is a basis for M sub 5, 1. Again, take note that the dimension of M sub 5, 1 is 5, 5 because we simply multiply the mn. So m 5 times 1, which is equal to 5. Also, the set S has 5 vectors. That is why it is sufficient to show only that the set S is linearly independent to conclude that the set S is a basis for M sub 5, 1. And that's the end of our discussion for for lesson 3.4, which is basis and dimension.